why are we taking a little bit of a sidetrack through talking about probability? Well, for the rest of the course, we're going to be using probability as social science researchers. Because what we have, most likely with our data, is we have data that is a sample, a subset, that comes from a larger population. And we're going to need to use that, that sample to represent our population. And I want you to think of it that way, okay? We can't ask every single American how they're going to vote in November. But what we can do is we can ask a large number of those people, usually around 1,500, and say, all right, you sample, how are you going to vote? And we use that sample to represent everybody. Does anybody here like watching TV? Like TV? I was like raised by TV. TV is like my parent. Mom, dad, and TV. Okay? One of the things that drives me crazy is when you're watching a show and it gets canceled because they say not enough people watch it. And you're like, wait a minute, I watched this show. What do you mean not enough people watch it? Well, what they do to calculate who's watching it is through a sample. There's a company called Nielsen's, and Nielsen's has a few different ways in which they figure out who's watching TV. One thing that they do is they have what's called a Nielsen family, and they put a box on top of your cable box, and it records, not like you're thinking like a VCR records, but it measures which channel you're watching at any given time. Okay. They also have a system of diaries. So I actually did this one time. I got really excited. They send you a diary, just this little book, and they send you a diary for every TV in your house. And at this time I had 4 TVs in my house. I'm like, yes. I'm going to make sure they know which TVs or which channels to keep. And you just write down what you're watching in 5-minute blocks. So Magnum PI, done. I'm watching Magnum, right? The Golden Girls, done. Right? I'm going to watch 9 straight hours of The Simpsons, done. Okay? What they're doing is they're collecting a sample. Right? They're trying to figure out the best guess of how many people are watching a particular television program. Does anybody here know what the most watched TV show is every year? No? Okay, it's a TV program that's on every year for the last 50-something years. The Super Bowl. The Super Bowl is the most watched television program every year. And how do they know that? Same way they know that nobody watched Firefly. It's a show none of you have ever heard of. Okay. They took a sample, and from the sample they say, okay, this is what we've calculated to be the sample mean. And using probability theory, they can say, yes, about 70% of households were watching the Super Bowl. Okay. This is what we're going to do too. We're going to use samples to make statements about the population. However, I want to highlight this last part. Right? Samples are imperfect representations. And a lot of time is spent on figuring out how to correct for the imperfections of collecting a sample. So we have to recognize that there's going to be a difference between our sample and our population. So what we do is we talk about probability in the normal distribution. Because remember, the area of a normal curve is 1. The percentage under a normal curve can be 100%, and probability has a maximum of 1. So these three coincidences that they're all the same under the area of a curve, we can use that to represent probability as well. So if you have a distribution, scores on a test, there's a reason we use that example with you, because you're familiar with what a test is and what a grade is, right? So the grades on a test, the percentage of the scores between a z of 0, which means it's where on our normal curve. If a z-score is 0, where is that on the normal curve? Guys, gotta watch that Lecture 5 video. Okay, the curve is centered at the mean. So if a z-score is 0, it means you're at the mean. Okay. The percentage of scores between 0 and 2.24. So a z-score is 0 out to 2.24 is the same as a person randomly being selected and having their score be between 0 and 2.24. So for us, when we use the normal curve, we're going to think of percentages and probabilities interchangeably. Why do we do this? Well, we need to do this because the mechanism by which social science works is through hypothesis testing. Now, with somebody in this room, I said hypothesis testing, and you probably had a flashback to like high school science, right? What's the weird stuff you guys did in high school science that you remember? There's things that I'll never forget, even though it was many years ago. Anybody ever do titration, where you have two liquids, and they're like, here's a clear liquid, here's a clear liquid, make them purple? And you had to find the right proportion of liquid A and liquid B when you combine together. It was usually like 2 to 1. And all of a sudden, like the magic liquid is now purple. Remember that? Okay, glad I wasn't the only one that did that. And they're like, you're testing a hypothesis. Actually, no. I hate to say this, but your high school science teachers were just wrong. So much of your high school education was just wrong. That's not actually the scientific method. Like, yeah, you're running an experiment. No, you're not. So what I wanted to talk about today is the scientific method for us, for social sciences. And we're going to talk about what a research hypothesis is and a statistical hypothesis. Because they're kind of the same, but there's a subtle difference between the two. So if you're to come to my office hours because you're worried about the paper that's due at the end of class, one of the first questions I'm going to ask you is, what's your research hypothesis? What is it that you're trying to study? And the example that I'll use, and which none of you can write a paper on, is, are there gender differences in spanking a child? That's my research hypothesis for this class. Are there gender differences when it comes to spanking a child? Now, I want everybody to think and ask themselves that question, and right, so you have it in your head. Are there gender differences in spanking a child? Raise your right hand if you say there are gender differences. Raise your left hand if you say there are no gender differences. Gender differences? No gender differences. Okay. For all of you who have your right hands up, say man or woman on the count of 3. Who is more likely? Did I do that right? Or did I just get confused and reverse it? Huh? That was right? Okay. Say man or woman on 3. Who is more likely to spank? Ready? 1, 2, 3. Did everybody say man? You didn't? Okay. You gotta say it with. Okay. All right, for those of you who said men, why do you think men are more likely to abuse their children than women? Because dad hit me. Mom never hit me, dad hit me. That's fine. Why? Why would men be more likely to hit their children than women? Why are men more prone to violence in general? Testosterone. All right? Men are amped up. Plus, culture teaches us that the tougher we are and we break shit, the cooler we are. Right? So you have biological reasons. You have culture reasons. All right? Is there any sort of parental role, any stereotypes about parental roles that might play into this? So let me reverse the question. Why would women be less likely to spank their children? Because they're nurturing and comforting. Think about the next time you get into an argument with your girlfriend, mom, somebody else. Wait, you're supposed to be nurturing and comforting. Why are you hitting me? Right? Think about that for a second. Okay? That's our research hypothesis. We're going to focus on just simply being able to explain our research hypothesis. Okay? So my research hypothesis is there a gender difference when it comes to spanking children? Or I could say, are men more likely to spank their children than women? Or are men more likely to support spanking children as a form of corporal punishment than women? That's just explaining it. That's the setup for my paper. A statistical hypothesis is going to focus on the math that I need to do in order to test this. My null hypothesis is that the average score, it's going to actually be a proportion, not a mean, but whatever. We'll get to that eventually. That the average score for men will be equal to the average score for females. So I'll say my null hypothesis is that there's no relationship between gender. That's what the M and the F are standing for here, male and female. An alternative hypothesis is that there is a gender difference, that the mean scores for men and women aren't equal. Okay. Now, let's say I want to make this a directional hypothesis. How mathematically do I say one is bigger than the other? Has anybody ever seen those before? How do they work? That's what they are, but how do they work? How do you know which one is which? But how do you know that? Come on, weren't you guys taught the alligator thing? The alligator what? Yeah, he wants to eat the bigger thing. That's how Abby was taught this. The alligator eats the bigger meal. I was taught it the other way. You point at the thing that's little. You make fun of it. 1980s, 2010s, right? So this is the bigger number. Bigger, smaller, bigger. Just remember that, right? Again, I'm trying to fix this and remember that the alligator eats the bigger meal and not that we're bullying, picking on the little one. Okay? So you could put these in. So for those of you who raised your one hand and said it was men, you would say, let's do alternative hypothesis 1, that the mean for men is bigger than, greater than, the mean for females. And for those of you who think that women are more likely to hit their children, you would write it this way. Okay. So in hypothesis 1, men are, the mean for men is greater than the mean for women. And in hypothesis 2, the mean for women is greater than the mean for men. Okay. I know, dusting off some middle school math skills here. So there's a process in place. This is sort of part of the scientific method, and we say that you have to follow these steps. So I'm going to pause for 10 seconds while you write down these 4 steps. It's okay to be a slide copier here. The first thing we have to do when we're doing research like this is we have to state the null and the alternative hypothesis. The second thing is we do statistics, which is why you're in this class, and you make a decision about the null hypothesis. Really, this is the one skill that I have to teach you this semester. Do statistics. Once you've made a decision about your null hypothesis, you're going to revert back to the topic that you're researching and draw a conclusion. Either men or women, or neither, are more likely to beat their children. And finally, you're going to relate the results of your analysis back to your research hypothesis and hopefully draw a conclusion to the larger field. Right? But again, we're going to focus on step 2 for this course. That's what we're trying to do. You done, slide copiers? Okay. What do I mean when I say null and alternative hypothesis? Well, let's focus on that idea of null. Right? Null. Null is another synonym for zero. We have a lot of synonyms for zero. Zip, zilch, nada. Okay? None. Null. The results are null and void. Void. Empty. Okay? Nothingness. Okay. So your null hypothesis says there is no relationship between the two things that you're comparing. There's no relationship between your independent variable of gender and your dependent variable of child abuse. Okay. No relationship. Now here's the thing, and the book has this weird example. So chapter 5, we're going to teach you how to use the standard normal distribution. And then in chapter 6, we're going to teach you about hypothesis testing, not using the standard normal distribution. Thanks, Howard. Appreciate that. He uses a different distribution, which is known as a binomial distribution. And a binomial distribution is when you flip a coin, right? You have two outcomes. It's either one or the other. And I don't want to teach you the binomial distribution, but I don't want you to get confused by what he's doing. So I'll instead of teaching you the binomial distribution, I'll walk you through the example that he uses in the book so that you don't get confused. And the example that Howard uses in his book about social and behavioral sciences is about football. I think it's time to write a letter to Howard. Howard, we gotta have a talk, man. And so Howard is testing the theory that you can predict whether or not a team is going to win a football game based upon the coin flip. Now, for our football fans in here, please explain to the non-football fans why the coin flip matters. Okay, so whoever wins the coin flip gets to determine whether or not they get the ball to start the game or whether they give the ball away to start the game, and then at the second half of the game, they'll get the ball first coming out of halftime. Is there any advantage, let me say, is there any other component to the coin toss that we need to talk about? Because there's one more. So the team that wins the coin toss gets to pick whether or not they get the ball. The team that loses the coin toss gets what? To determine what? The direction of play. So which, I guess, end they're going to defend or start from. Okay. Which in college football can be handy because of what? College football fans. Why would you want to determine which end zone your opponent is marching towards or kicking into their field goals? Yeah, you want them in the student section because they're going to be really loud when they're on that end of the field. So in overtime, you always want to go second and you always want to go towards the student section. Okay. All right. So let's just say there's a preference. But again, why couldn't they use the standard normal distribution? Instead, he uses this thing. A coin flip has two outcomes. It's a binomial distribution. So what is the probability of a head on one coin toss? We did this last week. One coin toss getting one head. 1 out of 2, 50%. Okay. His sample is 12 football games. Okay. So this is what the binomial distribution looks like. Anybody see a familiar shape in it? It's bellish, right? But it's not the standard normal distribution because it's a completely different mathematical equation that draws this curve. In this curve, what we are looking for is the probability that in 12 games, if the coin flip matters, we should have a very rare outcome. All right, if we're going to look at 12 games, that's the sample size that Howard uses in this example. If the coin flip matters, or it's an advantage, then they should probably win more than half of the games, right? When it comes to social science, though, we have a little bit more of a higher standard. When we're dealing with probability, right, we actually have settled on this idea of 5%. Alpha, which is the kind of sideways little squiggly ribbon, alpha is a statistic, a criteria that the researcher determines which one to use. What we, as researchers, have come up with is we typically use an alpha of 5%, 0.05. Why do we have to set an alpha? Well, we do this because we recognize that we have a sample and we don't have a population. And our samples that we draw from this larger distribution of the population, we could just get an odd sample. We could get a sample that's not representative of the full population. That's typically one of the first questions that people ask when they see a poll that has a result that they're like, really? Who'd you ask? Right? Who's your sample for this? Because you're trying to figure out why the result didn't meet your expectations, and you know you didn't ask everybody. How many football games are there on an average weekend? Let's just think about this for a second. Can we figure out how many football games there are in the United States on a weekend? Where would we start? You've heard of football, right? Not soccer, American football. You've heard of it, yes? Where could we start with trying to figure out how many football games there are on a weekend? Do they have football games on weekends? Okay. Huh? Is the Friday part of the weekend? From the police reports I see, yes, it is part of the weekend. There are plenty of arrests on a Friday night. So let's think about this. How many football games are there in the United States on a weekend? Okay, let's start somewhere. NFL. How many football games are there on an NFL schedule on the weekend? Let's say 16. There's 32 teams. They each play each other. 16 games. All right, there we go. We got a good start. Under the NFL, what do we have? College. How many college football games are there on a weekend? Let's say 100. All right, and that's just looking at the FBS teams. Then you have the FCS teams and the NAIA. All right, let's throw in another 100. Okay, so now we're at like what, 250. Are there high schools that have football teams? How many high schools are there in the United States? Well, there's at least 50 because we got 50 states. Okay, so let's say there's thousands of football games, right? And we got a sample of 12. I think he uses 12 Super Bowls in the book. So we've got just 12 Super Bowls out of the thousands of football games that are any weekend. And they all start the same way. I've never been to a football game that did not have a coin flip. Okay. So because of this, we have to say, listen, there's a chance that our sample is not very representative of the population. So to do that, the criteria that we use is going to be really small. And we've come to 5%. Okay, we've come to 5%. And what this is there's a 5% chance of us finding a difference when in fact there is no difference. Okay, so let's think about that for a second. We're going to have a false positive. We're going to say that there's an effect of choosing the coin flip or winning the coin flip, when in fact there is none. Okay. We want that to be really, really small. We want our mistakes to be really, really small. The best way for me to sort of underscore this, and we'll talk about it again later in the semester, is when you guys go to take a medical test, right, you want there to be a very, very small chance that that test is wrong, right? Like, when the doctor tells you you have cancer and you have 4 months to live, you want them to be really, really certain, right? Or that you're pregnant, God forbid, right? And you're like, oh my God, wait a minute, how accurate is this test? 99.8% accurate. Well, geez, I mean, there's a 0.2% chance it's wrong. No. Okay. That's one of the first things. Well, we get bad news. Well, how likely is this? Right? Are you sure? Like really, really super duper sure? Maybe I should take another test. Can we rerun that test? And they're like, sure, we'll get the same results, but if that's what you want, keep peeing on a stick. Okay. So we as researchers want to make sure that we're not giving out false positives and saying that there is an effect when there isn't. Because we don't want people to make other decisions based upon the fact that we had our tests wrong. So if we tell you that chocolate is good for your heart, or you'll live longer if you drink wine, we don't want a bunch of people going out there and like chugging down a bunch of wine and eating chocolate all day. Okay. We want to be sure of our results. Because what we're trying to do is we're trying to reject the null hypothesis. That's the decision that we're going to make. Right? Rejecting the null hypothesis. Now, the null hypothesis is the one that says there is no relationship. The null hypothesis says that the statistic that we calculated from our sample is not different enough. There's not a good enough probability of that happening, given the fact that we think the null hypothesis is true. So it's not just simply as easy as calculating the two means of the two groups we're comparing. All right? We don't actually just calculate a mean and say, oh, well, men, according to our survey, are more likely to hit their children than women. Because that's just saying what your survey results are. You're not comparing the likelihood of observing that difference in the survey if the null hypothesis were true. So back to Howard's stupid example in his book and the coin tosses. The way that this process works to make a decision is we have to have an outcome that is in the area of 5% likely. So looking up here at this distribution, where am I going to find that 5%? How many games do you have to win after winning the coin toss to be convinced that that we can reject the argument that there's no relationship between the coin toss and the football game outcome? Coin toss is 50-50. What's the potential outcome of a football game on any given Saturday or Sunday? 50-50, right? Two teams. One of them's going to win. We're not talking about ties here. Okay. So the most likely outcome when you play 12 games is that you win 6 of them. Right? That's the most likely outcome. If I wanted to waste a bunch of time, I'd hand you all a quarter and say, start flipping coins. And we'd see how many times out of 12 you would get 6 heads or 6 tails, right? Or we do a dice example. Same type of idea. Okay. So 6 is the most likely outcome. Where's the least likely outcome? 12, right? Or 0. Why 0 or 12? Because our distribution is... starts with the letter S. Has to do about the shape. You can do it. Symmetrical, right? Our distribution is symmetrical. So you are equally likely to win all 12 of those football games after winning the coin toss as you are equally likely to lose all 12 of those football games after you've won the coin toss. Make sense? Okay. So what you've now noticed is that because it's symmetrical, we've got to take that 5% and we've got to do what? The 5% of the least likely, rarest outcomes are where? They're on both ends. Right? So if I take 5% and I put it on both ends, how much? You know the answer to this. Go ahead. I've got 5%, but I got to put it in 2 ends. How much in each end? You don't have to do the math. Yeah, it's 2.5%. Okay, so here's what we do. Where is 2.5%? Well, I know the rarest outcome is winning or losing all of the games. So that's 0.0002. Plus 0.0029. 0.0029. That gets me up to 0.0031. That's not 2%. That's not even a percent yet. 2 wins plus 0.0161. Now I'm up to 0.0192. Is that 2.5%? No, that's 1.9%. So I'm going to have to get over to 3 to get to my 2.5%. Well, that's 0.5% on its own. All right. So in order, come on, there we go. But it's too much. It's too much on its own. So 0, 1, and 2, 10, 11, and 12 are all in my 5% area. So I took 2.5 on this side, 2.5 on this side. if the probability of what I observe is small, given the distribution, I can reject the null hypothesis. All right. This is our decision rule. All right? This is what we're saying. If the critical value of the statistic we calculate lies in that rejection area, then we will reject the null hypothesis. If the number of wins in 12 Super Bowls is fewer than 3 or greater than 9, we will reject the null hypothesis that there's no relationship between the coin toss and the outcome of the game. Otherwise, we can't reject the null hypothesis. I just have to do a warning here. It says do not reject. That does not mean the same thing as accept. You never, under any condition, whether you're being tortured, whether your loved one has been kidnapped, you never, ever accept a null hypothesis and say that there's no relationship. Why? Because your data is what? Your data is always what? A sample. Your data is always a sample. We do not want these 12 Super Bowls to represent the infinite number of football games that have happened in the United States of America and around the world. So that's why we don't accept the null hypothesis. We just have failed to reject it. This isn't some power of positive thinking bullshit here. All right? We don't want you to reach a conclusion where you say, no, there's no relationship between these two. Because if you do that, and you say there's no relationship between these two things, then people are saying I should drink more red wine. Right? Oh, it doesn't matter. There's no relationship. Okay? It could just be that your sample didn't reflect the relationship. Right? You got a sample that wasn't necessarily representative. Never, ever accept the null hypothesis. I will instantly fail you in your paper if you accept a null hypothesis. I'm done with you. Just not allowed to do it. Because what you're doing is you're saying, well, my sample's good enough. On the other hand, you've never actually proven anything. So if you say that your data proves the existence of a relationship, no. Because we're not a hard science. Like, you can't prove that there's a relationship between gender and beating your kid. You found evidence to support, right? Because really what you're doing is rejecting the null hypothesis that there is no relationship. Right? You haven't found a planet. Like, the hard sciences are like, look, that's Mars. It exists. I can prove it. Look at it. We go land stuff on it, drive around on it, right? You can't prove a relationship because you can't tangibly see it, right? So we're not proving anything, and we're not accepting any null hypotheses either. We're finding evidence that supports our research hypothesis. We're not proving that men are more likely to beat their children. Because it doesn't work that way. All right. Yeah, conclusion. All right. Yeah. Back to this idea. Only provide support or lack of support for a hypothesis. We cannot prove. We're not in, social science is not in the proving business. Because proving, when you prove something, you're saying that it's deterministic. Here you go. There's an SAT word for you. Deterministic. Gravity is an example of something that is deterministic. Okay. When I drop the pencil, it will do what? Fall to the ground. Every damn time. I have a cat, Daisy. Daisy likes to test gravity occasionally. She'll get up on something and she'll knock it to the floor. And when she does that, I'm like, yep, Daisy, gravity works. And I'll pick it up and put it back up, and what does she do? She knocks it back down again. She's like that Chumbawamba song. You get knocked down, I get up again. Like, stupid cat. Just let it. So eventually I just let her knock stuff down and be like, I'll get it later. I don't know what they're doing. The only reasonable explanation is that she's trying to, like, reprove gravity works. Like, yep, it fell. Let's see if this thing falls. Yep, this thing fell too. We're not in the deterministic sciences. We're not in the hard sciences, like chemistry, where when you get the 2/3 to 1/3 ratio, the two clear liquids turn pink. Like, they know that's going to happen every time. That's why your science teacher has chosen that experiment. It's not really an experiment. It's titration. We, as human beings, so we have determinism. We, as human beings, are stochastic. I love that word. It's like my life motto. Life is stochastic. And what stochastic means is randomness. Human beings are so random. I wish we were more deterministic. I wish I could figure out how to get my kid in bed. Because it doesn't work. The same thing does not work every day. There are too many variables in the John equation to get him into bed calmly and smoothly and quietly without the threats of giving away my TV. John is stochasticity represented in human form. How stochastic is John? John, what do you want for dinner? Spaghetti and meatballs. Make spaghetti and meatballs, put it down. I didn't want spaghetti and meatballs. Like, dude, you just said 5 minutes ago spaghetti and meatballs. Well, I didn't mean that. I meant breakfast for dinner. Like, oh my God, I can't do it. I can't deal with the randomness. And that's why men beat, no, I'm kidding. That's why men beat their children. All right. So when we're studying human beings, we have to allow for the stochasticity of that. The fact that we are all not robots, we all don't make the same decisions. And that an approach you may take with one person will not work with another person. All right, and this is the hard part of figuring out how to relate to other people. Some people like nicknames. I had a faculty member call me Papa Bear one day. Lost my mind. Like, I know I'm the chair of the department, but I ain't your Papa Bear. Like, that's not our relationship. Not the right context. It's difficult. It's hard. We're stochastic. We're random. And it can change day to day. I've been sick all week. I've been a different person this week when I'm sick than when I'm feeling good. The weather affects people's moods. It affects attendance sometimes, too. Right? There is that element of randomness to us. So that way, when we make a decision or a conclusion, and we say something as very specific as men are more likely to beat their children, we got to be really sure. We got to be 95% sure. right? Pregnancy test level sureness. Okay? Because what happens when you tell that person they're going to die in 4 months? What are their 4 months going to be like? They're going to make some decisions that have consequences beyond 4 months. They actually made a TV show about this, right? Some girl's told she has this terminal cancer, she's going to die, and she goes off and, yeah, it got canceled, didn't it? See, because not enough people watched it. What was the name of it again? Life sentence? No. Okay, life sentence. I thought it was like life, fine, that can be the name of it, right? And she's like, da-da-da-da-da, and she makes horrible decisions when she thinks she's going to die, right? She doesn't go to college, because why go to college? I'm never going to use my degree. She doesn't, I don't even think she finishes high school. I made it like 3 episodes and then I quit. She gets engaged to some foreign guy, not even thinking about like immigration issues, because she's going to be dead soon. And then what happens? Her cancer gets cured. Now, it's not like the false positive thing that I do, but she gets cured, and then she's like, oh, wait, I've set up this life, and now I have to live it out. It wasn't a really good show. Okay. So when we are doing social science and we're talking about how the world works, we have to be really certain, right? And there are 2 types of error. The one that we're really concerned about is rejecting the null hypothesis when we shouldn't. So saying that there's a relationship when there isn't one. The other type of error is when you have the criteria set too high. When you fail to reject the null hypothesis when you should. So you're not detecting a relationship in your data when in fact there actually is one. Of the 2, I tend to think the second one isn't quite as bad. And the reason I think the second one isn't quite as bad is because this means that we're going to have future study in this. So you're sick, you go to the doctor, you take a test, and you have cancer, but the test says you don't have cancer. Does that mean you're going to stop being sick? No, you're going to continue to be sick, and you're going to continue to go to the doctor, and you're going to continue to get tests to figure out why you're sick. And eventually they'll figure out why you got sick. This is, of course, informed to me by the television show House, where you get a diagnosis and then they keep just trying to find out what's wrong with you. And then 45 minutes later, it's not lupus and they fixed you. So when you don't find a relationship, all we're saying is our data didn't find it here. It does not mean it doesn't exist. So researchers will continue to look for that effect. The other thing, too, is we don't really publish those results. Right? So there's very rarely a time when you guys read a journal article that says there's no relationship. I could just sit down and write papers all the time about whether or not snowfall in New York affects the president's public opinion rating. And I could just find like all sorts of no effect. No effect, no effect. Well, guess what? That paper is not going to win the journal space. Saying that there is no effect between snowfall in New York and the president's approval rating is not going to get published. So people are still going to be sort of researching that area. So we're not even going to know about our journal failures because nobody's ever going to read them. So people will still look for a relationship even when you don't have one. We're going to come back to this later in the book, but I just wanted to sort of get this into your head now to understand what it is we're doing when we're testing a hypothesis. The other thing that we have to look at is sample size. Sample size matters. It's built into our testing. And generally speaking, we want to have a large sample size. this is actually a field now. This is a field that you can get into. We colloquially call it big data analysis. And programs that do scraping, do text scraping, for example. Like a Google word count. Google Trends. You ever heard of Google Trends? Well, you've heard trending on Twitter, right? Right? Well, how do you get on the trending list for Twitter? Yeah, more people are tweeting that, let's say, hashtag, right? So during the baseball playoffs, it's HR for HR. So if you guys are tweeting at all now, add the hashtag HR for HR, home runs for hurricane relief. And every time you do that, T-Mobile will donate $1 to the American Red Cross. Thanks. Okay. See? All right. So what it is it's counting, right? So Twitter is actually looking at what people are tweeting, and they're like, hey, we see this hashtag over and over and over again. Or a name suddenly appears in people's tweets, which means what? They're dead. Like, we start talking about a celebrity that we haven't talked about for 30 years. They're dead. You guys even know who Burt Reynolds is? It's the Bandit. Okay. So if something is trending, that means people are talking about it. That's because Twitter has a program that scrapes all of its tweets and is counting the number of times that a hashtag or a name gets used, and that's why it becomes trending. It's not like, I want people to talk about this now. That's not how trending works. It's an aggregate. During the Kavanaugh hearings, Google also keeps track of search terms, and people were Googling things like Devil's Triangle to figure out what it meant. And so Google also keeps a trending page, and you can see which search terms, the frequency in which search terms are being used. That's a Google tool that you can use. Political scientists are doing data scraping on websites, or taking PDF files and scraping them for word counts. So when I was in graduate school, there was a program that took party manifestos or party platforms and then scrape them for the word count. I do a project where I look at judicial advertising, and I can't scrape those files because they're all strange formatted PDFs. So instead we have to look for actual terms and read it and say if it was in the ad or not. But this ability to do scraping or using the internet as your data source has created this field known as big data. And so it's another sort of level of statistics. And the idea behind it is that we want our sample sizes to be larger because that gives us a better examination of the relationship between the two. A side effect, though, is it also increases the likelihood that you're going to reject the null hypothesis. So more data is actually better. So there are some data sets that I have that have 65,000 responses in them, and you almost always reject the null hypothesis because the uncertainty around the sample, given that it's a larger size, gets diminished. Alpha is what we call that criteria that we use, that 5% criteria. I talked briefly about this idea of directionality. So our alternative hypothesis can either be directional or non-directional. If it's directional, we're saying that the area of rejection is in one tail. So if we say that winning the coin toss makes you more likely to win the game, in theory, you could put all of that 5% in the more likely, the higher win total. That's a directional hypothesis. When you do this, we kind of think it's cheating. because you're packing all of the rejection in one area. It lowers the criteria for you to reject because all of the 5% is in one of the tail. So generally speaking, we like results to fit the non-directional hypothesis. So where you just say they're not equal. Back to the coin toss example, there is an alternative. There are actually two facets of the games that are changed by winning the coin toss. It's not just who gets the ball first, it's also which direction of the field you go in. So that would be an argument for a non-directional hypothesis. The fact that you could actually, the direction of the outcome, given the day with weather like this, those are the worst football games to watch because they just run the ball all the time. And it's like a 3-6 game. Because the one guy, they waited till the wind died down and they kicked a couple of field goals. Those games suck. You can tell I watched a lot of Big Ten football. Awful weather. Okay. Well, in that case, it might not be whether you get the ball first or not. Okay. So when we're thinking about constructing our hypotheses, we have to keep this in mind. Talked about that. Talked about that. Okay. So this is where we're headed. Okay. What we're going to do, not next week, because next week you're taking the midterm exam. What we're going to do in 2 weeks is we're going to start learning statistics where we can actually test hypotheses. And what the goal is to have us understand the relationship first between our sample and what we know the population to be. The examples in your book use standardized testing is probably the example in the book that they use the most. And the reason that standardized testing claims to know the population is because of how they distribute the grades. I'm going to take a couple minutes just to explain this real quick. So, and this goes back to chapter 5 as well. So when you have a distribution on a test, the reason we call it a standardized exam is how they calculate your score. I have a lot of students come to me to talk about the law school admissions test. The LSAT is an exam that has a predefined score between 120 and 180. They only give the test, I think it's 4 times a year. And so when they give the test out, they have the population of test takers. So let's say 10,000 students take what month is this? This is October. They take the next LSAT, which is in December. 10,000 people take the December LSAT. They're going to get a population and population mean, and they're going to get a population standard error. The mean score is not the 120 to 180. The mean score is the number of answers correct. So when you take a standardized test, answer every question. Don't leave anything blank. You take the LSAT, they score you, and they just want to calculate how many you got correct. Then what they do for that test, for all 10,000 people, they calculate the standard deviation. I'm making this up. Let's say the standard deviation for the 12-18 test was 8 points. Okay. They then take your score subtract that from the mean, and then divide it by standard deviation. That's what puts it on the curve, okay? Because this gives you a z-score. Your z-score starts at 0 and goes out this far. Say you did bad. Coastal students do bad on the LSAT. Average LSAT score is a 150 something. Average coastal LSAT score is a 145. You're back there. What your standardized score is your z-score. And then they give it a different number to make you feel better. Because nobody wants a negative score. I took the GREs. What'd you get? Negative 125. That just means you were less than average, right? If it's a z-score. But you don't want people to think that. That's why all these stupid standardized tests, like, what'd you get in your SATs? Well, 0 starts at where? Like 200? Right? You just take the test. You write your name down. You at least get a 200. Why? Because that's the minimum they gave you. LSAT does that at 120. Right. So when we say something is standardized, that means your score has been converted relative to the standard deviation, which is what we use. So it's at the bottom. Okay? Understanding that kind of helps you understand z-scores just a little bit better. All right? You have your study guide, work your study guide. Please do the section exercises. They look like quizzes at the bottom of each Moodle section.